Today we continue with our discussion on gyro compass and trying to understand how it works. This is part 3 of the video. In part 1 I discussed what is a gyro compass and what is a gyroscope, how does a gyro compass differentiate from a magnetic compass, the legal regulations concerning it. In part 2 we discussed about the properties of the gyroscope, which is the properties of gyroscopic inertia, rigidity in space and precession. And in part 3 we'll discuss how the properties of the gyroscope can be used or was used historically to convert the gyroscope into a gyro compass that can be made to point in a fixed direction for course keeping and direction measurement on board ships. Alright, I'll give you the link to the previous two parts in the description section below if you have missed it. So let's start with gyro compass or understanding gyro compass part 3. So a gyroscope, and that you saw before previously, based on the principle of rigidity in space or gyroscopic inertia, if a gyroscope was made to spin and if the gyroscope attained its maximum RPM based on its mass of the rotor, it could be made to point towards a fixed direction in space. However, it doesn't happen so because the earth on which the gyroscope is placed is also spinning on its own axis, and although slow, the movement of the earth has an impact on the gyroscope, because of which the gyroscope experiences a movement along the vertical and horizontal plane known as the tilt and drift. So today we'll be learning how the movement of the tilt and drift was compensated for historically through the use of weights, so that the gyroscope could be made to point horizontal, and basically to make the gyroscope not only seek north but also to settle north. This is also called stabilizing the gyro compass terrestrially. For the gyroscope to work as a gyro compass, there are three requirements that needed to be covered. The first requirement was the spin axis of the gyroscope should be horizontal. The second was that it should be made to point towards geographic north, that is 000 degrees direction. And the third one was to compensate for the movements of drift and tilt, so that it not only does it point north, but it also keeps pointing north. It settles at north and it doesn't drift or tilt away from that position. So the first requirement, for which the spin axis must be horizontal, is a relatively easy job to do. So you can make the gyroscope horizontal through careful construction to ensure that the unit is always balanced with the spin axis horizontal. Now what happens is, at this point when the spin axis is horizontal, there are two weights attached in the olden days gyro compass. I'll tell you what happens in the new days, in the newer gyro compass as well. But if you understand the concepts behind the olden days gyroscope and a gyro compass, you will easily understand the new days gyro compass or the modern gyro compass, which uses the principles of fiber optics and light, travel of light. All right, so I'll come back to the point that I was talking about, is making the spin axis horizontal. So we can keep the gyroscope axis horizontal in such a way that only when the gyroscope axis is horizontal, there are two weights attached to the gyroscope axis. At this point, when the gyroscope is absolutely horizontal, that is the only time the weights will be equally balanced. Anytime the gyroscope axis drifts out of the horizontal position, the weights will be unequally balanced. One side will become heavier than the other. So this was ensured through careful construction, where gyroscope was made horizontal and the weights were attached in such a way that when it's horizontal, it's absolutely the weights are balanced with each other. Alright, so the gyroscope would of course be made to point towards any direction and made the weights balance in such a way that because we need to point it towards true north, we could point it towards true north and make it horizontal, but the gyroscope could be made to point towards any direction, and in whichever direction will balance the weights, the gyroscope would have pointed, or rather settled at that direction. Later on we'll realize with the acting weights. So remember, the gyroscope is a man-made equipment. It doesn't point true north naturally. It is made to point true north. That is what I'm trying to convey here. So you can make it point to any direction if you want to, but because we want to make it point towards the true north for direction keeping and course measurement, we make it point towards 000, and only at 000 is the spin axis horizontal and the weights are placed in balance with each other. Outside of this, then the trouble starts to happen, and I'll talk about the trouble as well. The second requirement was to make the gyroscope point towards the geographic north. All right, so we can find out the geographic north direction. Of course, there are many ways to do it. The pole star is one of them, and there are other ways to find out where geographic north lies. So geographic north, pointing towards geographic north is not the issue. but keeping it pointed there was the issue, because the gyroscope, like I said, because the movement of the earth, whether the gyroscope is located at the poles or at the equator or any other latitude, the gyroscope axis, because of the movement of the earth, was experiencing a movement along the vertical as well as the horizontal plane. So the vertical plane movement was of course called the tilting, and the horizontal plane movement was called the drifting, and the drift was maximum at the poles and zero at the equator, and the tilt was maximum at the equator and zero at the poles. But on any other latitude there was some component of drift and tilt for which the gyroscope had to be compensated for. So once it was made to point north, it had to keep pointing north, otherwise it was drifting away from that direction because of the Earth's movement. Alright, so drifting and tilting away from the direction based on the latitude, of course. Now these weights that were attached had to bring the gyroscope axis back towards the north, and this was called the property of seeking, make the gyroscope seek north, alright, through the use of weights. This was not a very simple explanation, and I wish I could show you through a demonstration of the gyroscope. One day maybe I'll make a video on that. I have to make a live video on that to show you how the gyroscope axis uses the weights, but I'll try my best here to show it to you through animations as well. Alright, so the tricky thing with the gyroscope axis and the spin gyroscope is, what you will realize is that the weights actually use the property of the precession. So if you remember and you saw my last video, the precession is a property of the gyroscope where if you apply a force in one direction, the gyroscope axis moves, or what we call precesses, in a direction 90 degrees away from the direction of the force. And this was the property that was used to make the gyroscope keep seeking north and not let it drift out of north. Because if the weights, as soon as the gyroscope spin axis would drift or tilt away from the 000 degrees, the weight would act in such a way, and if you can visualize the weight acting downwards in such a way that the gyroscope axis would move 90 degrees from the direction of the force and precess back to 000 degrees. But the complication here was that the precessing back and the direction of the weight in which it was acting also depended a lot on the direction of the spin of the gyroscope. So the weight had to act in a certain way depending on whether the direction of the spinning was clockwise or anti-clockwise. So maybe one day if I can show you through a video, if the gyroscope is spinning clockwise, then the weight would have to act in a certain way for the gyroscope to spin or precess back to the 000 degrees if it drifts or tilts away from the 000 direction. And if it is spinning anti-clockwise, then of course the weight has to act in the opposite direction so that it precesses back. Alright, so many a times the gyroscope which was spinning in one direction would precess out of the 000 degrees and go towards east, and the gyroscope axis would tilt in such a way that the forward part of the axis would come up and the aft part of the axis would go down, or and when it would precess towards the west, the opposite would happen. The forward part would tilt down and the aft part would tilt up. So naturally the weight had to act in such a way that the gyroscope axis was precessed back to the required direction depending on whether it precessed to the east or west. So this was the tricky part. Alright, now that is where two ways of making the gyro seek north came into play. One was the bottom heavy method invented by a famous scientist who was known as Brown, and the top heavy method which was invented by, or rather introduced by Sperry. Sperry actually worked with the initial makers and patents of the gyro compass. I discussed this in the first video. So basically what they realized was they could make the weights act in such a way then that the gyroscope axis would precess back to the north if it drifts or tilts away from it. Alright, the problem with the bottom heavy method, and I'll talk about that very soon. There was a problem with the bottom heavy method because of which a top heavy method was introduced. Alright, and I'll discuss that very soon as to what was the problem. Alright, now for small angles of tilt, precession was directly proportional to the tilt. The greater was the tilt, the faster was the precession. The weights, initially the weights were used, weights was used initially so that the weight would act and make the gyroscope precess back to the north. but the weights were very slow to act, because of which the use of weights was then replaced by a liquid arrangement. And this is where I'll talk about the top heavy and the bottom heavy arrangement and why it failed. Now, what was happening was that Sperry introduced the top heavy mercury control arrangement, where as soon as the gyroscopic axis or the gyroscope spin axis tilted or drifted out from the north direction, and say if it drifted eastward, it would tilt upwards, the north end of the axis would tilt upwards and the south end would tilt downwards, the mercury would flow based on the gravity. So as soon as one axis tilted upwards and the other axis tilted downwards, mercury was used. The mercury would flow from the top end to the bottom end, making one end heavier. When one end became heavier, it started to act like a weight. As soon as it acted as a weight on the bottom, on the south end of the axis, due to precession, the gyroscope axis would then precess back to the north, 000 degrees direction. All right, but for this the axis had to spin in a particular direction because the mercury would only flow based on the gravity. So if the spin axis was rotating in not in a clockwise but anti-clockwise direction, the same principle may not have worked, because the mercury had to always flow from the top of the axis to the bottom of the axis using gravity, and only the weight would only act on the bottom axis, which was downwards, so that it would precess back. But that depended on the spinning of the gyro compass, the direction in which it was spinning. So to counteract for this method, the bottom heavy oil control method was introduced by Brown, and what this did was it was an improvement over the mercury method, because mercury would only flow with gravity. So the gyroscopic spin axis had to spin always clockwise, and so that this would work. But with the bottom heavy control, the gyroscopic axis could spin clockwise or anti-clockwise, it didn't matter. The reason being that when oil was used, the oil could be flown from the top end to the bottom end using gravity, but it could also be made to flow in the opposite direction using motor pumps. All right, it would go against the gravity as well using motor pumps, and that's why oil was used. So irrespective of in which direction the gyroscopic axis is spinning, it could be clockwise or anti-clockwise, based on what it was required, the oil or bottom heavy oil control could be adapted to suit to the spinning direction of the gyroscope. So if the movement was such which is required the oil to flow by gravity, then that would be used. Otherwise, they would use motor pumps to transfer oil from a lower end to the higher end, going against the gravity, so that the weight acts in such a way that the gyroscope axis would precess back towards the north or 000 degrees direction. The reason oil was used and not water, because the oil is safer for electrical components. Remember, the gyroscope involved a gyro motor which was spinning at a very high RPM, and there were a lot of electrical parts involved there. So if water was used and if water leaked, then it would cause short circuit or electrical problems, and that's why oil was used, and oil made it easier to flow around as well than mercury. Mercury is much heavier, it's more viscous, it cannot be made to flow with a pump. All right, so this was how the property of precession was used, and the property or the use of weights was used, so that the weight acted on the gyroscope spinning axis in such a way that whenever it drifted or tilted out of its horizontal 000 degrees direction, it would be made to bring back to the 000 degree direction. As time evolved, the use of weights was not only replaced by mercury and then oil, but slowly as time evolved, they were replaced by electromagnetic sensors and torsion wires. When I started sailing as a cadet, many gyro compasses were using these electromagnetic sensors and torsion wires, and you could hear the clicking sound. So basically, the electromagnetic sensors and torsion wires were doing the same job as that of the weights, that when the spinning axis was horizontal and 000 degrees, they would be made taut, and whenever the gyroscope axis would precess out, these torsion wires would immediately act in. So the whole reason was that over a period of time, the use of weights was replaced by mercury and then by oil and then by electromagnetic sensors and torsion wires was to make it act fast. As soon as the gyroscopic axis would precess or drift or tilt outward from its 000 degrees, it had to act fast. The weights had to act in very fast so that it could be brought back towards 000 degrees, because the gyroscope, the risk could not be taken of the gyroscope precessing out from 000 degrees, because it would affect the course keeping and the direction measurement as well as the steering of the ship's compass. The last bit of the gyro was not only to make it seek north but also to keep it settled at north, and that is where the principle of dampening the gyro came into play. Now what happened was that the gyroscopes over a period of time, if switched off, the gyroscope would lose its RPM of 60,000. All right, at 60,000 RPM is pretty high RPM, revolutions per minute is very high. It was 60,000 or 30,000, I kind of forget, it was 30 to 60,000 RPM. Now the gyroscope had to attain that RPM for it to be able to use the property of gyroscopic inertia and make it point towards one direction in space, or one direction, that is 000 degrees. All right, until it attained that RPM, it would wander about. That was called a wandering gyro. Or as soon as it lost the momentum or lost the RPM, the gyro, like a spinning top, used to start to wobble around, and that was called a wandering gyro. And that is why in the olden days, when the gyro compasses were switched off in, say, dry dock, or it experienced a power failure, or for some reason the gyroscope for servicing as well, when the master gyro was switched off, you had to switch on the master gyro at least 4 hours before vessel's departure. The reason was that it took the gyroscope a long time to gain that particular RPM at which it would be made steady and horizontal and the weights would be balanced before it could be used for any kind of steering. Alright, now that is not the case with modern day gyro compasses. I'll tell you why it is so, and that is where I will just introduce the fiber optic gyro compass. So that is not the case with the modern day gyro compasses. Alright, so the olden days the RPM had to be attained. It took over 4 hours for it to attain that RPM, and during that time, because the gyroscope had not attained its maximum RPM, it would wander about. That is, it would seek north, but it would not settle at north. So it would make kind of a spiral movement around the direction of the north, as you will see here, and this would keep happening till the time the gyro would attain its maximum RPM. It would wander about. Or it's like a spinning top. If you think about a spinning top when it has its RPM, it keeps spinning, but as soon as it starts to lose its momentum, it starts to wander about, it starts to wobble, and that is what the gyro did as well. And that is where the dampening method of Sperry and the Brown came in, which was adding a weight to the horizontal plane of the gyro so that it comes into the effect when the spin axis has any kind of tilt movement, causing a precession in the vertical plane so that it not only seeks the north, but it settles at north as well very quickly. And the dampening method of Brown, which assisted in the precession towards the meridian, and it came into effect when the spin axis had tilt, and it opposed the precession when the spin axis passed the meridian. So by meridian, you know what I mean by meridian of 000 degrees. All right. So these were the two dampening methods that was used, because the gyro was not only required to be seeking north, but it also had to be settled at north as quickly as possible. Now, over a period of time, of course, the settling period has been reduced, and this is because the gyroscope has started to use what we call is the fiber optics gyro. Alright, so you can see now the settling time has been reduced from 4 hours to almost 30 minutes, and sometimes even less than that. The reason is because fiber optic gyros, they use pretty much the same principles, except that in fiber optic gyros the use of fiber optics cables are made, and instead of weights or anything like that, what it does is basically it splits a light atom and makes the two light atoms travel towards each other and make it point, and they meet at the north end, which is towards the 000 degrees. And this movement of light, because this, and as soon as that happens, the gyro starts to seek north, because it is based now on the principle remains the same, but the light that travels through the fiber optics cables does the settling of the gyro through the splitting of the light atom, and the light travels much faster than any other medium that was used to make the gyro seek north. So that is why the settling time has reduced drastically for fiber optic gyro, but the principle basically remains the same. It still needs some kind of settling time as soon as it's switched on, but it has reduced, and that's why gyro compasses today can be switched on, and when they're switched on they can be used immediately, but depending on whether your ship is still using the olden days gyro compasses or the modern day gyro compasses. All right, so I leave it at that now, and I hope that in the last 3 videos you have gained some understanding of the gyro compass. It's a bit of a complicated topic to cover, and especially in the absence of any kind of videos or animations, I find it hard to convey what I'm trying to say here. So I hope you liked the videos, and even if you didn't, just let me know. But if you did, just send a like and let me know through your comments on how I did, and what other topics you want me to cover, and whether something was amiss here or not. All right, I'll see you guys with my next video very soon, guys. Bye, and study hard, work hard.